Alright, good evening everyone. Welcome to the PMRF TA session for the course Signals and Systems. This is week 10, Signals and Systems, week 10. So the topics that have been covered in this week are as follows: discrete time convolution sum, then the discrete time convolution sum examples and certain properties, then LCCDE representation of discrete time LTI systems. Then we have impulse train sampling, which is followed by reconstruction of continuous time signal, and then this week's last topic is the important Nyquist sampling theorem and aliasing. Alright, so let's start solving the previous year's assignments, which will help us in preparation. So first of all, this is a knowledge based question. A continuous time delta function is known as dash, whereas dash is used for the discrete time delta function. Alright, so this doesn't have much concept involved and it's just about names. So if you remember the continuous time delta function, which we denoted like this, so its property was it was equal to 0 when t was not equal to 0, and was infinity when t equal to 0, and the area under this delta function is 1, and this is actually called the Dirac delta function, which is meant to be continuous time. Okay, and then we have the same discrete delta function, which actually behaves like this: delta n equals 1, okay, when n equal to 0, and it's equal to 0 when n not equal to 0. Okay, so this function, this delta function, discrete time, does not have any singularity. That means this function does not go up to infinity or does not become undefined at any instant of the discrete time index n. And this is actually called the Kronecker delta function, which is in discrete time. Now the solution is continuous time delta function is known as Dirac delta function, whereas Kronecker delta function is used for the discrete time delta function. All right. Now let's move to the second question. Let xt be a signal with Nyquist sampling rate of 2 omega naught. What is the Nyquist sampling rate for yt equals to derivative of x with respect to t. Alright, so before we get to solve this, I shall briefly discuss the Nyquist sampling theorem. Okay, so let us consider signal xt, which is continuous time in nature and band limited. So the corresponding spectrum, let's say x of f, it looks something like this. Okay, so its bandwidth is actually b. Okay, now what do I do? What kind of sampling are we talking about? We are talking about impulse train sampling. So how does an impulse train sampling look like? So whenever you have a signal xt, okay, which let's say looks something like this, then what do? We sample it at instances like this. Okay, so 0, t, 2t, 3t, so on, minus t, minus 2t, minus 3t, and so on, and the resultant signal looks something like this. X of t, which is the sample version of xt, looks like this. It's just filled with impulses at multiples of t, 2t, 3t, minus t, minus 2t, minus 3t. All right, so how do we actually define such a function mathematically? So we have xt coming in and we have some analog multiplier, and then it gets multiplied with a sequence called the impulse train st, and we get excess of t. So how does st look like? St is simply the strain of impulses of unit amplitude and separated by an interval of time t, minus t, minus 2t, so on. What is the expression for st? So st is summation of shifted Dirac delta functions over the entire time interval. So you can write st is summation over k equals minus infinity till infinity delta t minus kt. Okay, because this is delta t, this is delta t minus capital T, this is delta t minus 2t, this is delta t minus plus t, delta t plus 2t. So the index k represents the kth multiple of t. Just hold on a second. So now what is excess of t? Excess of t is x of t multiplied with s of t. Let us bring in this expression over here. Summation over k equal to minus infinity to infinity delta t minus kt, taking x of t inside the summation, x of t delta t minus kt. Now what shall we do? We shall use the shifting operation. What is the shifting operation? Shifting operation means x of t times delta t minus a equals x of a delta t minus a. So the direct delta function only shifts or selects the value of x at the time instant where it is located. So this direct delta function is located at time instant a, so it captures the value of x at a and removes everything else because the function is 0 everywhere else. So the direct delta is located at kt, so comes x of kt delta t minus kt. Alright, so now how does the spectrum of s of t look like? So you see very carefully, s of t is a periodic signal, isn't it? Because excuse me for the interruption, it was unexpected, sorry. Periodic signal with the period t. Okay, so now what happens? We can write s of t as a sum of m equal to minus infinity to infinity c of m e to the power j 2 pi f m t. Okay, so we are writing it as the exponential Fourier series, and c of m, if you try to evaluate it, so if you take a small interval between minus t by 2 to t by 2 over here and try to find out cm will actually be 1 upon t. Wait, let me check. So cm is actually integral 1 upon t integral of minus t by 2 to t by 2 s of t e to the power minus j 2 pi f m t dt. So s of t is actually delta t, so it becomes delta t minus 0, so I get 1 of t. Okay, cm is 1 upon t, so I can write st as 1 of t summation m equals minus infinity to infinity e to the power minus j plus j 2 pi mf t. Now how can you write this in the frequency domain s of t? So it becomes s of f equals 1 upon t summation m equals to minus infinity to infinity. What is this? Exponential, and you know exponential 1 in frequency domain turns time domain turns out to be 2 pi delta f in our frequency domain, isn't it? So So e to the power j 2 pi mft will mean that we have 2 pi delta, it will be f naught, where f naught is 1 upon t, or I can write delta f minus m f naught. Okay, so what is the spectrum of excess of f? We know that this is the multiplication of xt and st. So in frequency domain they will correspond to a convolution, so it will be convolution of x of f times s of f. Let me mark this that this is convolution in frequency domain. Okay, so we have x of f as it is being convolved with 2 pi upon t summation m equals minus infinity to infinity delta f minus m f naught. This come out 2 pi upon t, m equals minus infinity to infinity x of f convolved with delta f minus mf naught. Now you know that xt when convolved with a shifted version of delta function shifts the x of t or x of f directly to that point where the impulse is located. So what will it be? 2 pi upon t summation m equals minus infinity to infinity x of okay, so actually I am doing in the f domain, it's not in the omega domain, so this 2 pi won't be there. It will actually be 1. Okay, so here it will be delta f. Okay, so it will be x of f minus the shifted position mf naught. So how does it actually look like? So if we look at it carefully, let's say that our original x of f had a unity peak spectral value. So now x of f will actually be shifted versions. Okay, the excess of f actually we will have a scaling of 1 upon t. Okay, scaling factor of 1 upon t over here, and here this is shifted versions. Okay, so let's say we have one copy for m equal to 0, a copy for m equal to 1, a copy for m equal to 2, and so on. And here a copy for m equal to minus 1, we have a copy for m equal to minus 2, and so on. Alright, this centered at 0, this centered at f naught, this centered at 2 f naught, this is centered at minus f naught, this is centered at minus 2 f naught. Okay, and let us look at these sequences. This is b and this is minus b. This is f naught, so the extreme left side will be f naught minus beta, and this is f naught plus beta. Now let's look into this portion very carefully. This portion, now I have drawn a case. There are multiple copies of xf, right? And the parameters b and f naught have not been discussed to a great deal of what should be chosen. So if we want to ensure that these two, the signal over here, the spectrum over here remains the same as the one that I'm showing over here, that means this is discrete, this is distinct, and there is no overlap. So what should we do? What should condition should be ensured? it should be ensured that this frequency should be lesser than this frequency. Okay, this should be lesser than this. What am I saying? B must be lesser than f naught minus b. So in that case, what happens? The ending point is before the starting point of the next spectrum. Okay, so there is some gap between these two. So what does it mean? F naught must be greater than 2b naught, 2b. This is the Nyquist sampling theorem. So F naught is the sampling rate. F naught I mentioned earlier was 1 upon t, inverse of the sampling time, and B was the signal maximum frequency. Okay, so Nyquist theorem states that the sampling rate must be at least twice the maximum frequency content of the signal. Alright, so this is the famous Nyquist sampling theorem. And what happens when the Nyquist theorem is not satisfied? So this is, let's say, b is over here, and in the other case what happens? F naught minus b is less, so it starts before the other spectrum stops. So we have this region of overlap, and this is called aliasing, where two parts of the spectrum overlap and there is loss of information. You will never ever be able to recover back this signal. Okay, so this is called aliasing, and it takes place when Nyquist rate is not satisfied. F naught is less than twice b. This is the condition when the aliasing takes place. There is loss of information and Nyquist rate is not satisfied. You lose information. Okay, so we have look at this, and you have already covered question point 4 and point 6 in this small period of time. And how do we reconstruct this signal when we have this excess of f when I want to recover back this signal? Okay, this actually later goes on to the digitized form. Okay, so after you have sampling, you have something called quantization and all those stuffs where you convert the and then you have actually the digitization where the frequencies are limited between 0 to 2 pi. So we'll talk about that later in the upcoming lectures when we have the digital frequencies and the Z transform concept coming. Now let's suppose we have this sample signal and I want to get back the original signal. What should we do? We have to remove the other parts, right? Other things. So what should we do? Simply use a low pass filter. Okay, a low pass filter. Okay, means FL and FL, these are the cutoff frequencies. So you have to ensure that it is sampling rate is, that's why ensured to be higher than twice the bandwidth, so that the filter cutoff frequency lies between this. And you know that real life filters have some roll off and such characteristics. Order of the frequency, order of the filter determines the cutoff, the roll off. So because of the finite roll off, the filter cannot have an abrupt edge from some value to 0. Okay, it will gradually decrease. in order to allow the space for gradually decreasing, we make assured that the sampling rate is high, significantly higher than the twice the bandwidth. So what we will get back is our original signal, and this is the reconstruction from the digital signal or the sampled signal. Okay, so now getting back to our original question which we were trying to solve, we had xt, which was a signal with Nyquist sampling rate 2 omega naught. So Nyquist rate being 2 omega naught means that the bandwidth of the signal is omega naught. What is the Nyquist sampling rate for yt equal to dxt dt? Okay, let's draw a picture. So 2's solution, so let's say we have minus omega naught and omega naught as the frequency components, highest frequency component of x of omega. Okay, now what is being asked? We have yt equal to dx of t dt. So what will we get in Fourier transform? Y of omega equals j omega x of omega. So what is its magnitude? Y of omega equals to mod omega x of omega. So how will it look like in this case? We will be multiplying it with mod omega, right? So mod omega looks something like this. So initially omega is 0, so it will be 0. So slowly and gradually omega increases, so we get the image of x of omega in picture, but x of omega again drops to 0 at omega naught. So even if you increase omega, the omega naught, x of omega after omega naught becomes 0, so it stays as it is. Same with the other side, it is symmetric. So in this case also the bandwidth of the signal is omega naught, so the Nyquist rate, I will denote it as nr, is twice the bandwidth or 2 omega naught. So yt equal to dx dt also has the same Nyquist rate as the signal xt. Okay, question 3 is once again a repetition of this, but in a different way, that you have this xt with fund bandwidth omega naught. Now you have the integrated version of xt. They are asking what should be the sampling rate. Okay, now let's proceed in the same way. We have x of t whose Fourier transform is x of omega. Now integral, now in case of integral what happens, you are convolving xt with u of t. So in frequency in the Fourier domain we have multiplication, x of omega into u of omega, is x of omega times 1 upon j omega plus pi delta omega. Okay, how does it look? X of omega by j omega plus pi x of omega times delta omega. Delta omega will shift it at omega equal to 0, so we get x of 0 delta omega. Okay, so how does this spectrum look like? Y of omega, so it's like, if you ignore this Dirac delta thing, it will be mod x of omega upon omega. Okay, so let's say we have some very high value at omega equal to 0, there is a singularity due to this Dirac delta function, and then we have some very high value, but omega naught remains finite. Omega remains finite, it is 1 upon omega. Okay, but all of a sudden after omega naught it becomes 0 minus omega naught omega naught. So over here also, because x of omega mod x of omega equals to 0 for omega greater than mod omega greater than omega naught, bandwidth equals omega naught, so the Nyquist rate becomes twice omega naught. But what have we been asked? What should be the sampling rate? We have not been asked the Nyquist rate. They are asking what should be the sampling rate. So our answer should be the sampling rate must be greater than or equal to 2 omega naught. Why? Because sampling rate can be greater than this. It should be, practically it should be greater than the Nyquist rate, because of one of the reasons that when you want to reconstruct this, then the low pass filter, which has a finite roll off, that has to be compensated, that has to be taken care of. So that's why it's greater than equal to. And in case you get this such a question or a similar pattern of question comes in the exam, and there's one option which says equal to 2 omega naught, and you select that, then you lose the marks, because there will be another option called greater than or equal to, or greater than only, because the greater sign will suggest that you should go at least in this or much better than that. Okay, so this is the answer. Now let's move into the next question. Question 4. Question 4 states the same thing. Xt has bandwidth omega naught. Now you have yt equals 2x of t plus 3 x of t minus 3. You have to find the required sampling rate. Now the thing is that it's the same pattern as the previous one. So x of t has a transform x of omega, so y of t has the transform y of omega equals 2x of omega plus 3 e to the power minus j omega x of omega. So 2 plus 3 e to the power minus j omega x of omega. How will this look? X of omega, its modulus will look like this: minus omega naught to omega naught. Mod y of omega is mod 2 plus 3 e to the power minus j omega x of omega. So now you see this 2 plus 3 e to the power j omega, this is less than or equal to 2 plus 3 of omega, 5x of omega, or whatever be the term. Okay, this term will always vary between 2 minus 3 to 2 plus 3. That means it can be anywhere between x of omega till 5x of omega. Okay, so if x of omega is like this, then 5x of omega is like this, and so the combination y of omega, although I can draw it deterministically, but just in order to give you a flavor of what is happening, how to evaluate things without going for the actual calculation, I am showing this. So it will be somewhere in the between, isn't it? Something like this. I mean, it won't be so abrupt or hazy, but what I'm saying is that the values will remain between these two triangles. Okay, so you see there is no effect on the bandwidth. The bandwidth still remains the same, and hence mod y of omega, or the y of omega, still has a bandwidth omega naught, and as a result the resulting sampling rate must be greater than or equal to twice omega naught. Alright, so you see in all the cases, irrespective of the kind of operation that we have done, be it the derivative, be it the integral, and be it the addition, shifting, linear combination, we get the sampling rate to be 2 omega naught. But that may not be the case always. There might be other cases like modulation, multiplication, convolution. In such cases you are very likely to see a different sampling rate. Okay, so I leave that as a homework to you to find that if you convolve xt with itself, okay, like xt convolved with xt, find its Nyquist rate. Okay, that's number one. Then xt convolved with cos omega naught t, find this Nyquist rate. This is also homework. So it should not be convolved, it should be a multiplication. And then xt multiplied by x of t upon 3. Yeah, so x of t upon 3, so you will have, yeah, so yeah, for all these three cases I give you a homework to find all the Nyquist rate for all the three cases. Alright, so this will be a very interesting exercise for you, and this will also boost your confidence, especially question number 3. Okay, 3 may look abrupt, but think about it, think about convolution in a different way, not the integral form. Okay, all right, so any doubts so far, please let me know. Fine, let's look for the next question. Question 5. For an input signal x of n equals 2 to the n u of n with a signal impulse response hn equals un, find the output signal y of n. Okay, this is a question of discrete time convolution, and we shall solve it in from first principles. So yn is x of n convolved with h of n. How does it look? You have x of n going into a system described by the impulse response h of n. You get an output y of n. How do I write it in terms of summation? Break it up. K equals to minus infinity till infinity x of n minus k hk. Also the same if you interchange between x and h. So whether to choose h of n minus k or whether to choose x of n minus k, that depends on what are the individual functions, how do they look like, and which one will be easier to calculate mathematically. Okay, so in this case if you see, x of n is 2 to the power n and h of n is with un and h of n is un. So you see which is easier, x of n minus k or x of k. It's obvious x of k is much simpler, so I would rather go with that. Okay, so y of n equals summation over k equals minus infinity to infinity x of k, which is 2 to the power k uk times h of n minus k, which is un minus k. Now we have to look at the unit step functions. Okay, you have to take the look at the limits. U of k, when is this entire bracket non-zero? The entire bracket is non-zero when k lies between 0 to infinity. Okay, and when is this bracket non-zero? The impulse response, this is non-zero when 0 lies between n minus k to infinity, or k lies between minus infinity to n. Okay, now both of them have to be satisfied, this condition and this condition. So you see in the number line of k, one condition is telling me that it should be from 0 till infinity, and the other condition is telling me that it should be from minus infinity till n. Okay, so which one satisfies both the constraint? This interval from 0 to n satisfies both the constraints. Okay, so k, which ranges from 0 to n, will satisfy this in both the cases. In this scenario, both u's will be equal to how much? 1. So 2 to the power k. Now isn't it bit familiar? It is 2 to the power 0 plus 2 to the power 1 plus all the way till 2 to the power n. Now I will use the GP series. So GP series, what was the formula? A plus AR plus AR squared plus AR to the power n minus 1. This summation is A into R to the power n minus 1 upon R minus 1. In this scenario, A is 2 to the power 0, which is 1. R, which is the common ratio, is 2 to the power 1 by 2 to the power 0, that's 2. AR to the power n minus 1 is 2 to the power n, which means R to the power n minus 1 is 2 to the power n. Well, is that correct? N equals to 1, so 2 to the power 1, 4, 1 plus 2, 3. It should be R to the power n. So R to the power n is 2 to the power n plus 1. So the summation y of n will actually be A into 2 to the power n plus 1 minus 1 by 2 minus 1 equals 2 to the power n plus 1 minus 1. Okay, and all of this is actually valid when n is greater than 0, because otherwise things are starting from 0, right? It starts from u of n, this one also starts from u of n, so y of n should have the un component as well, 2 to the power n plus 1 minus 1 un. Alright, so this is our output of the LTI system. Alright, now let's look into question number 6. So question number 6 states that for a linear constant coefficient difference equation, so called LCCDE, the response is IIR if, okay, so we'll not discuss this like in a question answer way, I'll rather do it in a different way. So any general system, what is this LCCDE? So when we look at differential equations, what is the form of a general continuous time differential equation? So in continuous time we have something called the differential equation, which describes the dynamics of a system, okay, or this impulse or how the system behaves with time. So the continuous time it looks something like this: dn, the nth derivative of yt, n minus 1th derivative of t, then the first, all the derivatives till the first and itself, equals to, then comes the input bm, the mth derivative of xt, the m minus 1th derivative of xt, b1 dxt dt plus b0 xt. Alright, now this is for differential equation for continuous time. When you have discrete time, you have something called dE, but this is actually called the difference equation. Okay, so in continuous time we have the derivatives which is called differential, but in discrete time, since we don't have the time being continuous, we only can consider the difference between the index, different index points 0 1 2 3, xn minus 1, xn minus 2. Okay, so we write something called the difference equation. So for example, this differential equation is given to you. You remember, if we remember our problem solving session on Laplace transform, so there we had shown you how to convert this into a Laplace transform. So if you look at this, you can directly find the transfer function very easily using the Laplace transform. So an s to the power n plus an minus 1 s to the power n minus 1. So you find it hs, which is ys upon xs, that will be ratio of two polynomials in S. Similarly, when we will do this Z transform in the last part of our course, we are already in the last part of our course, only 2 weeks are left. So in that case, we will be able to see that we will get a similar polynomial in terms of the Z variable, which is analogous to the S in the continuous time. So this actually looks something like this. So in a very short, we can write, we can write summation k equal to 0 till n a k y n minus k equals summation k equal to 0 till m b k x of n minus k. How does that look like? It looks like a0 yn, a1 yn minus 1, a2 yn minus 2. This is the output and its delayed samples, so on till a n minus 1, y of n minus 1, n minus 1 plus a n y of n minus n. And this will be equal to b0 xn plus b1 xn minus 1 plus b2 xn minus 2 plus bm minus 1 x of n minus m minus 1 plus bm x of n minus m. So you can see, we can actually write yn as a linear combination, or as a function of, which is a linear function of xn minus 1 till xn minus m, and yn minus 1 yn minus 2 till yn minus capital N. Okay, this is the first part of input, which is the input and its past values, and this one is the past values of output. All right, so now you can see that there are two contributions of yn, the input and its past values and the output and its past values. So there are two kinds of systems. One is the finite impulse response, or FIR. So such FIR systems are said to exhibit Hn as some B0 delta n plus B1 delta n minus 1 plus so on till Bm delta n minus m. So the impulse response has finite number of non-zero values. Impulse response has finite number of non-zero values. Okay, so zero, 1, 2, minus 1, minus 2, 5, 6, 7, 8, and so on. Let's say this is 1, this is 1/4, this is 2, this is 3/4, this is 0, and then after this, after 5, it becomes 0. Okay, so our Hn, if it may look like 1, 1/4, 2, minus 1, 1/2, 3/4, only this much. So if it is having finite number of non-zero samples, the in case that if that's the case with the h of n impulse response, then the system is said to be a finite impulse response. Okay, and this happens, and you can define it in this sense that ak equal to 0 for all k greater than 0. Okay, so you have no contribution of the output term or output's past values, because when you have output also coming, a fractional output coming, then you have the recursion, you have the feedback taking place, and whenever you have feedback taking place, it is never going to end. It will keep on showing its effect till infinity. And since the even ak is, at least one of the ak is not equal to 0, then that time the feedback takes place, the yn minus k starts showing its effect. Then we say that it is a infinite impulse response. Infinite impulse response, or IIR system. So Hn will actually be summation k equal to 0 to infinity h of k delta n minus k. So one such example that I can show you over here is Hn equal to 2 to the power minus n. Okay, 0, 1, 2, this is 1, this is 2 to the power minus 1, 2 to the power minus 2, 2 to the power minus 3, 2 to the power minus 50. So this is never ending, it dies towards infinity, and this happens when ak not equal to 0 for at least 1 k greater than 0. And why does it happen? Because yn actually becomes a k plus summation of all bkx of n minus k limit k prime equal to 0 to m. Okay, so it is because of this is called feedback, and this feedback always tries to give in some kind of input. So even let's say after my xn becomes 0, even if xn becomes 0 after some time, so this part may die down to 0, but because we have the past values, that past value will keep on feeding, and even if it goes down, it will keep on feeding forever. Okay, so that's why we have this infinite impulse response. All right, so we do one small thing, for one small shortcut trick for convolution, after which I'll stop. So let's say you have two finite length signals, 1 3 2 4. Okay, 0 is over here, that means this is segment -2 -1 0 1. Okay, and then you have x2 as -1 0 5 -7. Okay, let me add another thing to make the lengths unequal. This is our 0 index, so this is -1 0 1 2 3. Okay, so when you have two discrete time signals of length n1 and n2, okay, so what will be their convolutions length? Let's say y equal to x1 convolve with x2. The length will actually be n1 plus n2 minus 1, and in this case it will be 4 plus 5 minus 1, and that's it. And how do we determine the, and since it will be 8 link sequence, we have to also locate where is the 0 and d1. Okay, so when you have the, suppose you find the convolution, I'll tell the procedure very soon. Let's suppose you get some numbers a1 a2 a3 a4 a5 a6 a7 and a8. Okay, we have all these 8 numbers. Now you are supposed to find, you have to also find the ordering, right? Which one is the 0th sample, which one is the first sample, right? So how do we do that? We take the index of the last sample in x1, we take the index of the last sample over here in x2. Okay, add them, -2 -1, that's -3. The first finite sample that you get after the result process is the -3. Okay, I take the first non-zero sample over here, note its index, first non-zero sample in this, note its index, add the two indices, that becomes the index of the first sample of the result of the convolution. Now for however the last one. Okay, now you will be able to find the last one, I don't need to tell you, but just for verification, this is 1 for the last one, this is 3 for the last one, 1 plus 3 equal to 4, so this one is 4. So you see, -3 and 4, so this also verifies that we have 8 elements, and this matching our n1 plus n2 minus 1. Okay, so you'll have 8 elements. And how do we find this a1 to a8? Let me tell that now. You have x1, so let's put x1, the elements of x1 in a row, 1 column, 1 3 2 4. Okay, now let's put the elements of x2 in a column, in a row now, -1 0 5 -7 -2. Now in each and every element or position of this matrix, wherever they intersect, multiply the row and the column. What am I saying? I am over here, it corresponds to row of 1 and column of -1. And what is 1 into -1? -1. I'll write that. Now where are we? Row of 1. Let's say I want to calculate the value over here. How will I find? I will go over here, check this value, go upwards, check this value 5 and 3. I'll multiply 3 with 5, that is 15, and substitute that over here. This is the process, very simple. Minus 1, 0, 5, minus 7, minus 2, minus 3, 0, 15, minus 21, minus 6, minus 2, 0, 10, minus 14, minus 4, minus 4, 0, 20, minus 28, minus 8. Now we have completed this matrix. Now we will draw diagonals. How? From here to here, from here to here, second to second, third to third, then over here. I hope you are getting the pattern. Here, here, here. Okay, we have all the diagonals. Now we need to add the elements in a diagonal. First diagonal, nothing to add, we have minus 1. Second diagonal, minus 3 and 0. Minus 3 plus 0 is minus 3. Third diagonal, minus 2, 5. Minus 2 plus 5 is 3. Fourth diagonal, minus 4, 15, 7. Minus 4 plus 15 plus 7, that's 4. Then 10, minus 21, minus 2, that's minus 13. 20, minus 14, minus 6, that's 0. 28, 4, minus, so that's 32, and this is minus 8. This is our convolution. Now as I mentioned, minus 3 was over here, then this is minus 2, this is minus 1, this is 0. The fourth element is the 0. So the sequence, this is our 0th element and this is our convolution. Okay, so I hope you have understood the entire process of discrete time convolution and also everything about Nyquist sampling rate. So that's it for today. Thank you everyone for your kind attention.